your flow also this time. So the idea of this review sessions is basically to go again through the slides, through the concepts, really briefly, really quickly, and then essentially do additional analysis and additional exercises. Also to get them on the next level to basically do an hour exercise, which usually also then comprises the practice lab, which for today's case is practice lab 3. Good. So you have on the module the 3 PowerPoint presentations for the 3 chapters of t-distribution. You have an Excel spreadsheet that basically will contain the examples. So we're doing 3 examples today. Then we have practice lab 3, a solution code, which essentially I will walk you through today. That basically redoes the analysis of the 3 examples in the Excel spreadsheet. And then we have a t-score table that you all have and know how to read in the meanwhile, hopefully. And good. Please download all these files and open RStudio. Is there still anybody who cannot download and install RStudio? I think all the problems have been resolved now, right? So I'm evaluating now for a summer course how to use R online, and there's actually on RStudio there's an online version in the cloud in case somebody needs a workaround. But thankfully nobody does need that anymore. But now moving. Nothing to download. If it works on your computer and you have a valid version of RStudio, then you don't need to download anything. And it's particularly hot in here today. Okay. So, but let's get started. Let's briefly walk through the 3 different t-tests that we did. And I think the best overview of these 3 tests is really found on this slide. Because it basically gives you also the distinction between a STAT test and the t-test. And keep in mind, you have the single sample tests. That's a STAT test and a t-test. In this concept, you have one sample, you characterize one mean of that sample, and you compare that mean to your population mean or any other reference value. That doesn't have to be the population mean. It can just be okay, I have a sample of 15 students. Are they significantly different from 50? Knowing that the population has a standard deviation of 10. That would be a STAT test because you have the standard deviation of the STAT test given. If you have, I have a sample of 15 students and I want to compare them to a reference value or population mean of 55, and there's no standard deviation given, and you have to determine the standard deviation yourself, then you think t-distribution, because that allows you to estimate the standard deviation and use a mathematical modification with using the degrees of freedom rather than the sample size for the calculation of the variance, allows you to use this modified correction, this modified equation, to essentially get you to an estimate of the standard deviation of the population. That makes you think t-distribution. And keep in mind when thinking of that, of this particular graph, and that's my favorite graph. Actually, I showed that actually to graduate students because I like this graph so much. So let's assume you have here the blue normal distribution. That's the normal distribution. That's like, it's not really a perfect normal distribution. I actually would have thought it's more bell-like. But essentially you have with the blue, you have the perfect normal distribution. Let's assume it's perfect. And you have with an increasing sample size in your sample, a distribution that starts to resemble the normal distribution. And that means it essentially does approach these tails and it approaches the shape. So essentially the larger the sample size, the more higher that center becomes, because the center is where the bulk of the data is, right? So if you have a mean and that mean of your sample is really reflecting the population mean, with a larger sample size, you're going to bulk up the middle of your data because that's the most common values, right? These are the values that are most common in a sample, and this will center around the mean if you have a normal distribution. So this is where you're bulking up, and then you approach in terms of relative frequency, you approach the normal distribution here in the middle, and then the variability kind of shapes, and this is why you're modifying it by n-1 rather than n, because n is naturally larger than n-1, because you want to push the variability a little out. So you want to extend the span width of the normal distribution to resemble more what you would expect from the normal distribution. So that was one of the questions essentially on the exams. Now that was actually the other group. The question was, if you have an increase in sample size, does the variability increase or decrease? So the variability decreases, right? And when you then have a standard deviation, and you have the standard deviation and you have a higher sample size, and you're dividing the standard deviation by the square root of the n, disregard the square root, because still a greater n will result in a greater denominator. Therefore, your standard error of the mean, if you have standard deviation divided by square root of the n, your standard error of the mean will be larger with a smaller n or a larger variability. And if your standard error of the mean is larger, your test statistic, your t or your set, will always be smaller because the denominator is larger. On the contrary, if you have a larger n, your resulting standard error of the mean is going to be smaller because the denominator is now relatively larger. And consequently, your test statistic will be larger. If the denominator is smaller, the test statistic gets larger. Make sense? It is, and this is why I think it's so important for this class to have a little bit of Excel knowledge and a little bit like the opportunity. And I mean to take away the shyness of you to use Excel, because you can in Excel, you can just easily simulate it. You just basically, you take one value, you punch in that formula, you change it through with the ends, and you can play these scenarios through. And you can literally, you can see it visually, and then it helps you. It's like, I personally am very visual. It's easier for me if I see a dynamic within something that I simulate myself. It's easier for me to conceptualize it and to kind of memorize it. That's why I think Excel is such an important part of this class. And that's why I believe so much in these hands-on exercises. Although I don't know who of you actually take the time to go through the spreadsheet, I highly encourage you to do it, because there's a reason why I'm doing them. Okay, so T distribution approximates the set distribution of the normal distribution in order to essentially create a scenario that is comparable for hypothesis testing as you do with the set test. So now back to this. Okay, so we have now the two scenarios: single sample set test, single sample T test. It's one sample that you're comparing to a population mean or a reference value. Your comparison distribution, and this is where the key is, and that's step one in hypothesis testing. You're comparing the distribution of the means. The distribution of the means, meaning essentially you have the normal distribution, and then you're subtracting your reference value or your population mean as the reference value. You're subtracting that. And this is a constant. So you're subtracting constant from a distribution. Essentially, nothing else what happens, but the numerical value will change. And you still have the same distribution. And then you're standardizing it. And then you just look for the extremes. And then if your population mean is in the extremes and your test statistic is greater than those critical values, ta-da, you have a significant difference. Paired sample t-test, same concept. You have before and after. You have two different situations. Now you're creating, you have two samples of the same participants. These two samples, you're converging, or you're kind of, you're collapsing it. You're collapsing it arithmetically to one sample. by calculating a difference. That gives you basically the distribution of mean difference scores. That is your comparison distribution. And you're comparing it against whatever you're assuming to be true under your null hypothesis. If you assume no difference from before to after, your quote unquote reference value or your null hypothesis is 0. So that's when you compare your test statistic to a critical value, assuming that 0 is your reference value. So you're subtracting from your mean difference from before to after, you're subtracting 0 from it. And then you're standardizing this difference. Well, obviously you can kind of ignore the 0, but if you have a reference value that is not 0, like you have, for example, if you have I don't know, you have a population of toddlers that you're testing from month 1 to month 6, where you know they will be growing, like most of them will be growing, and you test them against a minimum growth, an expected growth of 0.5 kilos, for example. You basically, well, it's a little for 6 months, but so you have this reference value and you're subtracting this reference value from your mean difference. And you're dividing that by your standard error of the mean, derived from your difference. So you get your standard deviation estimated from your difference scores, and you're dividing that by the sample size, square rooted. That gets you to the standard error of the mean. And that's the standard error of the mean of the distribution of the mean difference scores. Fourth, independent sample t-test. And that's where everybody cringes a bit. And I understand, it's a little bit more complicated. But you have two samples. You have two samples that are independent from each other. It's not the same participants. There's no before and after. It's two independent samples. Sample A, sample B. What you do, you create a distribution of differences between means. So now you're doing a different exercise. You have your two different samples. You take out a little subsample of this and you create these pairs of differences. And you get these mean differences. And these differences between means is what your comparison distribution is. So it becomes mean of one sample and mean of second sample. Under your null hypothesis, these two means are null. So it's one minus the other. That's your null hypothesis. So you have mean 1 minus mean 2 minus, and this is now your null hypothesis, that the mean is 0. So mean 1 equals mean 2 equals 0. If you're expecting a difference, then you're subtracting that expected difference. And we will do the exercise in Excel again. But the comparison distribution is the differences between means of little subsamples of both groups. And then you do that weird calculation where you have degree of freedom and you have this partial degrees of freedom, this proportion of degrees of freedom, and you're creating this weighted variance. You're putting this together, you create one variance, and you're basically utilizing this for the calculation of the standard error of the mean. So that's the pooled variance approach with unequal variance. If you have unequal sample sizes in each group. And we will do this today. So this is really this, I'm flagging this table. Please make sure that you have this reviewed. So this is basically step 1 in hypothesis testing. And then it really comes down to you doing the steps correctly. Let's go through the steps. Okay. So you identify your population. This is where you need to know whether you have one population comparing it to a reference value, or you have one population before and after, or you have two independent populations. Then you have the distribution. It's comparison distribution of means, a distribution of means, comparison distribution of mean difference scores, or comparison distribution of differences between means. That's the independent sample t-test. And then you have the assumptions, parametric tests. All of these that we're doing, except for the chi-squared, are parametric tests. So the population data, notably, we don't know if the population is normally distributed or not, but we're assuming it to be normally distributed. In many cases, it may not be normally distributed. In most cases, you kind of get away, particularly with larger sample size. If your sample is above 30, you always get away with parametric tests. Keep in mind the magic is 30. And this is basically, you can easily see why. When you look at the t-distribution table, we remember of the normal distribution with the set of equals 1.96. You start off, if you look here, so again, one-tailed is the top row, two-tailed is the bottom row. You're looking for 5%. You're going through the degrees of freedom, and you see that it will decrease with increasing degrees of freedom. Up until 30, it gets fairly close to 1.96. Not really close, but fairly close. Where it gets then identically to 1.96 is with a sample size of 500. And it converges with the normal distribution curve in infinity. So those are the assumptions. The next assumption is normal distribution, random selection, independent measures. They're not affected, they're not associated with each other. And they're somewhat in their variability comparable. Yeah, we get to that. Then we state a null and research hypothesis. That really depends on the question. If you have a paired sample t-test and you're assuming that there was no change from before to after, then you would state on a null hypothesis that before and after was identical. So before minus after equals 0. That would be a null hypothesis in a paired sample t-test. In an independent sample t-test, it's basically mean 1 equals mean 2. In a single sample t-test, it's mean 1 or mean identical to mu. Also, don't mix up the distinction between mean and mu. So we have the mu in the population, mean in the standard in the sample. Same with the standard deviation. We have SD or S and SEM. And then in a population, you would have sigma. So these are the null and research hypothesis. Research hypothesis then is that there is a difference. Or with a one-tailed hypothesis, you have a directional difference. And we have done that. We can do this today again. Then you determine the characteristics of the comparison distribution. That's basically where you calculate the standard deviation, and you utilize this by dividing it by the square root of the sample size to get to a standard error of the mean. So this basically means it's your estimate of how much these means will differ from each other in terms of varying around a mean estimate. The critical values we're basically reading from either a t-score table, a z-score table, or from a t-score table. We've just looked at one. If you have 5%, you will find it in this row. If you have 5% in a one-tailed test, you basically will find it in the second column. I think that's considerably simpler. Keep in mind, degrees of freedom are basically determined based on the sample size in one sample minus 1. If you have 2 samples in an independent sample t-test, keep in mind you need to utilize the degrees of freedom total. You calculate this degrees of freedom for each sum of squares. So the idea is that you have a list, that you have a variable, and you have a list of individual entries, and you have a sum of squares for this list, well, basically which is the squared deviation from the mean. And this sum of squares basically allows you now that relationship between all your variables, and that sum of squares allows you to drop one entry, which is somewhat the redundant entry. So you drop for each of your entries, you always drop 1. If you have 2 variables, which is all the entries for group 1 and all the entries for group 2, you drop 2. So your degrees of freedom for an independent sample t-test is calculated as the sum of all participants in both groups bless you, -2, -1 for each group. So you calculate the sum of 2 different degrees of freedom. Don't get confused with that. There may be some questions where that is asked from you. So this is how you determine the critical values. Once you have the critical values, you can calculate the cutoffs. The cutoffs, hypothetically, you can label the cutoff a 95% confidence interval in the context of a 5% alpha. So there was one of the questions which several of you asked me for, and I forget who asked me, who had it, and I forget who first was hesitant to give you the points. So there was the question is like, so you determine whether you reject the null hypothesis based on a dot level. So it's a little tricky because alpha and p level is not really the same, because the p-value is that risk, that probability for the type 1 error to occur based on your test. The alpha is basically a fixed value, which you a priori, before you even do any analysis, determine to be that alpha for your analysis. So if you say 5%, that's your alpha, that's your acceptable type 1 error. Whereas the p-value is then the actual calculated type 1 error risk based on the differences based on the sample size. So they're essentially different. But the question was phrased in a way that both kind of were correct in a way. So I gave these points. But yeah, it's important to distinguish those two. So the p-value is not the same as the alpha. The alpha is just one possible p-value that you are willing to accept. That's important to keep in mind. So calculating the test statistic, this is where you calculate the t. And then based on that, based on your critical values, you make a decision. And that's the same for all 3 t-tests. Good. What were the additional exercises? Always keep in mind how to calculate an effect size. The effect size is a representation of a difference, a standardized difference, but standardized by the standard deviation rather than the standard error of the mean, which basically gives you an estimate of this difference and how much that difference actually counts, irrespective of the sample size. With the conventions that you know already, keep in mind the Bayesian approach. Bayesian approach, there won't be many questions about Bayesian statistics. Keep in mind when you have a question that kind of questions you about factoring in a prior belief into making a decision, this may be shooting in that direction. So keep that in mind when it comes to that. There are not many questions on that. Just some superficial, very easy ones. Good. Paired sample t-test, we talked about this. Keep in mind what an order effect is. So an order effect is if you're testing a before to after situation. So let's say you have change in weight and you start an individual with an exercise program, and then you test a second period. So first 6 months exercise program, then another 6 months. You're testing the difference from before to after, and then you have it the other way around. So it will present different, right? So you're getting an order effect for the order in which that intervention or that whatever distinguishing factor was in there is applied makes a difference. So if the participant's behavior or any part of the dynamic that you're actually testing is affected by the order of which the independent variable, the levels of the independent variable is administered, if that makes a difference, then you may have an order effect. The way how you counteract this is by counterbalancing, where you minimize that order effect by changing basically in which order that individual has gotten the different levels of the independent variable. Is extremely important for within groups design, and you have situations where you have like crossover studies, where you have like You have one starting with the exercise program going in a non-exercise period, then the other way around. The other individual starts in a non-exercise period, goes into an exercise period. You randomize them in each group, who starts with what, and then you basically you can tease out the true effect. And you tease out the true effect by basically having the subject as his or her own control. So you have the own individual as kind of his own reference. Gets you a very true effect of the efficacy of your intervention. So within groups design, actually very nice design, if possible. What did we have here? So these are the additional topics. Others just effect size. Okay. Any questions on any of the aspects of T distribution? I think if you understood the concept, this table answers most questions. If you're comfortable with that table, you're basically on top of all the other questions that may come your way. Just make sure you, yes.
Last class, like the formula, from your slideshow, was it in order of steps? Like the formulas?
You mean the spreadsheet that we did?
No, like on the slideshow, you had a sheet like you had a slide just titled formulas, and then you had a slide titled like steps for the calculation. So I want to know if the formula thing was
this one.
Yeah, all those. Are they like in order?
Yes, they should be. They need to be. I never compared. Or not. Okay, so 5 stages to this process, they say. Calculate the corrected variance for each sample. Step 1. That's what we did here. So this is the corrected variance. So this is S square 2, S square 1 or X. That's the corrected variance. Then we come down to the next step. We're doing a pooled variance. So you're pooling the variance. That's step 2. Then you have step 3. Convert the pooled variances from the squared standard deviation by dividing the pooled variances by the sample size. This is what we did here. That's this one. That's step 3. Then we have that's actually step 3 and 4. And then we calculate the square root of this form of variance. I would not have referred to it as a variance, but it probably quantifies. So this is this. So that's step 5. So that's 3 and 4. So 3 is basically each individual standard error of the mean, so to say. Adding those up, that's step 4. Square rooting it is step 5. Yeah. Okay. Good. So example. Okay. So we almost thought we did that. Yeah. So the examples are not. Yeah. They kind of. So you probably have more exciting example in the courses. So these are not the most sophisticated examples. So okay. So you have 8 students that basically write 2 exams over the course of a semester. The question kind of indicates it's the same 8 students. You have 8 scores. 1, 2, 3, 6, 8. And you have an exam 1 and exam 2. So the difference is now exam 2 minus exam 1 gets you now differences for each one of them. Now you calculate an average, you calculate the standard deviation. And it's as easy as could be, right? So you have an average and you have a standard deviation. Okay, So you know your population is basically those 8 students. Your comparison distribution is the distribution of the means of the difference scores. You have a null hypothesis. H0 is basically your before minus after. Before minus after equals 0, right? If you would assume an improvement or a worsening of the scores, you would say before and after equals minus 0.2. This is how you would basically re-express or rephrase your null hypothesis. So if you do HA now, you have before minus after is unequal to 0. So that's your null and research hypothesis. Now you need the critical values. That's simple, right? So we have 8 students, so the degrees of freedom, keep in mind, it's not 2 samples, it's only 1 sample because your comparison distribution is the mean of the different scores. So 1 sample. So that's 8 minus 1. 8 minus 1 is degree of freedom is here 7. Your critical value here is 7. Let's assume 5% alpha is 2.36. So your critical values is 2.36. So your cutoffs essentially can now be calculated by calculating 95% CI. So if you do lower limit, upper limit, you do lower limit, you calculate the mean minus the critical value multiplied. Now you want to characterize your comparison distribution. You do that with a standard error of the mean. That's basically your standard deviation divided by the square root of your sample size, which is 8. So this gives you a standard error of the mean of 2.007. Your lower limit is now your average minus 2.36 multiplied by the standard error of the mean of 2. It gives you a lower limit of minus 3.49 and an upper limit of average plus 2.36 multiplied by 2.007 gets you an upper limit of 5.99. What can we already conclude? So your null hypothesis is 0. Under your null hypothesis, this difference should contain 0, but it doesn't. Oh, it does. So your null hypothesis is true. So you will not be rejecting your null hypothesis. So this is, we are now calculating a test statistic. Still we're doing, so this would be this 1.25 minus 0 divided by our standard error of the mean. So our t is 0.62. So that's how simple it is. So if we were to calculate now the effect size, same story, 1.25 divided by the standard deviation gives us an effect size of 0.22. There's actually an effect size, a small effect size, but it's not significant because the sample size is too small. If you were to do the same analysis now, let's say you have 1,000 students and your degree of freedom is now 999. You calculate that now with a critical value of 1.96. You calculate that with a standard error of the mean of standard deviation divided by square root of 999. Oops, plus 1. That was my error last time. You have a standard error of the mean of 0.18. So if you calculate the t now, you basically have 1.25 divided by 0.17 or 18. Gives you a t of 6.96. Just to illustrate how important the sample size is, because it basically will rapidly boost your statistical power. So if there's a difference and you know from the effect size that there is some form of a difference, and notably the effect size is still the same. So if you want, so because this remains absolutely the same, if a larger sample size, that basically will lower your variability, and thereby you will find a difference, significant difference. That is the problem all statistics in large data sets suffer from. That's why it's important to also, so the effect size is really allowing for you to understand what difference do I really see here? How much does that really weigh? And it really comes down to what's the clinical, what's the practical significance? Not only the statistical significance, but what's the practical significance? If I have a difference in an exam score of 1.25, did my students really improve? No. And that's really what it comes down to. Is like it's the same as like in my world, I look at blood pressure data and I have blood pressure data from 1 month to another month, and the change in a population of 100,000 people was 1.25. That's not a change in the blood pressure. That's not a clinically or biologically relevant, statistically significant difference. So that's really what's important to keep in mind here. Okay, so there was this. So now I want to quickly show you the same exercise in R. So if you open practice lab 3, you have here on line 1, you have once again something that is commented out. So you clear the environment. You can now in line 2, you remove everything from the environment. You have in 1017. Sorry. The R code. Practice Lab 3 solution. It's a module 15 on Canvas. So this basically just creates you. So line 6 and 7 is basically just creating the data frame. But the data, excuse me, the data frame looks the same as the data frame in Excel. So basically you have the same value. It's again exam 1 and exam 2. And this data frame command is essentially just giving you those different values. And that's how easy you can create these data frames in case you ever choose to do so. And you're interested to enter data, you can just easily put this together. So it's like you label it here. This is basically the same as an equal sign. With data.frame, you tell R to create a data frame. And then you're just putting it together in that format here. With C, you're telling it, okay, so just put several values together and put it in one object. And that's what you essentially do. So if I just take this, I basically just get a list of data. And that's all I say. It's like, okay, create a data frame. That in the quotation mark becomes my variable name, and everything in the C, that's what I want you to pack into that variable. So that's how simple it is. If I were to make, let's say I want to add exam 3, and I enter now the values for exam 3, same thing, I just added exam 3, right? That's how simple it is. It's very simple code. But just copy exam 2, you can do that. Let me show you. You copy here exam 2, just this whole thing. You separate one variable from the other with a comma. You press enter and you just copy exam 2 in there and then label this to exam 3. That would give you a third exam. That's how simple it is. It's those of you that are a little bit inclined to learn more computer programming, that's how you simply like play around with it. Well, exam 3 is just you put a comma after exam 2 and you're telling R, okay, so there's something more I want to tell you. And then you just copy exam 2, that exam line, that same line. You just copy it there and you change 2 to 3. That gives you exam 3. Yes.
Can you turn to the lab and class? Do you want us to run our thing with all of these things you're adding throughout the class?
Well, if you want a smiley face, yes. No, no, it's go with the completed code, but please follow along. It's like I'm not doing it for no reason. It's like if you want to learn R to some extent, yes, it makes sense. If you send me just the solution code, I want you to have the code. I want you to have downloaded the code, and I want you to have run it once. That's really the idea. If you're never going to touch R again, it's like I know this is like an exercise that is non-valuable to you. I recognize that, so it's really up to you. It's just something I'm offering. Yes. That is, you just need to select. So you're making the comma. You select now exam 2 and all that C. You go after the comma and you press enter, and then you just copy it there. And then you just need to override 2 with 3. That gives you now exam 3.
Unexpected token.
An unexpected token. That sounds exciting. Okay. I said this really not getting rid of.
They're not meant to be like.
You're missing. There's one parenthesis too much. Before that comma that you inserted, that one parenthesis needs to be. Yep, that should work. So this is just playing around. So since we have a review day, this is just a nice exercise to do. Okay, so this is how you do that. To complete the confusion, now please delete it and just rerun the whole thing. So if you rerun DF1, it basically, no, you can actually leave it in. You don't have to delete it. Leave it in. Now you put so much work into creating this additional variable. Leave it in, please. So nothing. Okay, so you added now exam 3. So now you have 3 variables in there. Now we're going to go on and we're going to create now our first t-test. And we're doing this with line 13. If you added exam 3, it will be line 13. If you didn't add line 3, it should be line 12. That's basically the line where it says t-test, df1 exam 2, comma, df exam 1. Yes.
Did you run 8, 9?
Yes, we did. Just run it. It should create the data run. Okay, so t-test. And that is the reason why we're actually doing this exercise, because I want you to see, and those of you who will never program R, you may never use R, and that's fine. But what you certainly will have at one point in your life, if you further your career, your academic career, and you go somewhere where you will need statistics, you may be facing something like this. And that is a so-called statistical output from a statistical software. And that looks different for different softwares. This is the format of R, and there's a format from SPSS, there's a format from SAS, there's a SysStat, you name it. There are so many different softwares out there already. I chose to show you R. So basically what you see here, you need to go line by line through what you're actually seeing. And we will do this exercise with exactly these practice labs for you to see what information R is giving you. And all of this is very intuitive because all of this we have discussed and calculated. There will be some statistical outputs that are not as intuitive, and you will see which ones I mean. But that gets like chapter 16 and 17. So we have a paired t-test. R actually tells you it's paired because we have told R to conduct a paired t-test. So it basically, why is that important? Because if we don't say paired equals true, it will run an independent sample t-test. Will it give you a comparable result? Yes. Will it necessarily be as accurate as it should be? No. So if we're taking this off, this looks different. So now we see a Welch two-sample t-test, which is wrong. We know it's wrong. The results are somewhat the same, but the huge difference is the degrees of freedom are different. Therefore, the t is different. So there are a couple of caveats to be kept in mind. So this is a paired sample t-test. Don't delete the paired here. Okay, so yes.
So then how, if it's still the same amount of n?
Yep.
Then how's it different? Than when it's true?
So that is a very good question. The answer to that is that R is not calculating things the way we're calculating it, because it basically recreates the shape of the function. And then it approximates it and it estimates it the other way around. So what we have done was our approach is less of an approximation, it's more of an approximation. R is literally using the functions to model this out. So there's a lot that runs in the background. So the results will be somewhat the same, but R is just much more precise than compared to what we did. So the Welch test is actually a continuation of that independent sample t-test that we did with the unequal variance. So the Welch test is, yeah. So that's the long and rambling answer to your question. So, but this is not a distinction you need to really pay attention to. But yeah, so R calculates is more precise by basically using mathematical functions to estimate. It's the same when it comes to the calculation of the median, for example. R is not doing it as simple as we have done it. It basically models out the whole thing based on the variability, and then it creates like this perfect median. So they are.
So this is more exact than it's
Yeah, correct. So, but all ways lead to Rome. So it's like it gets you to the same end in some shape or form. Okay, okay, paired sample t-test. You can now, this t-test is just the printout of the t-test. Line 15, there we pack this t-test into what is called an object. So the object is basically nothing else but, well, it's an entity. It's some object where you pack anything in there. You can pack a data frame in there, like we did. You can pack a couple of numbers in there, as we did before in previous practice lab. You can pack a t-test in there. If you pack a t-test in there, you get now an additional object here in your environment, which you can click on the magnifying glass, and you basically get a list of stuff that's in there. And that's actually quite nice because you get a list of all the great stuff that's in there. So you get the statistic, which we know is 0.62. We get the degrees of freedom, we get a p-value, we get a confidence interval, -3.5 and 6, which we have calculated. Then we get an estimate 1.25, we get a null value, which is null. You could change that in R. You can give a new reference level, but we're not going to do this. Then you get the standard error of the mean, which we have calculated as well. You get an alternative hypothesis, which you can change to a one-sided hypothesis. Then you get a method, which is a paired sample t-test, and we get differences between these two. So that's t-test df1. You can specifically ask R how to get different things out. And ls is a command where you query R, okay, what does this contain? So if you say lsdf1, it gives you here the 3 different variable names that are in df1. If you say ls t-test df1, it gives you different things that are contained that we have just seen before when we click on the magnifying glass. And this is back in the days where this fancy RStudio was not around. You only worked with this. So when I started programming R, I basically worked only with this. So LS was basically your saving anchor, where you basically helped yourself on, because this gave you a list of things that were included in your object. That's what I'm showing you. Because you can, with this command, you can extract specific parts that your model contains, or that t-test contains, your object contains. So if you say t-test p.value, it basically will only extract you the p-value, which is that line. That's line 18. If you say t-test conf int, it basically gets you the confidence interval result. If you say t-test conf int bracket 1, it only gives you the lower limit. If you say 2, gives you the upper limit. If you write something like this, and you don't need to do this, playing around now a bit. I just want to show you what you can do, and hypothetically you can, oops, okay, that's a little too long. So this is sometimes useful when you create reports. You can automatize reports in R that basically print you a report out automatically. Okay, stuff. Good. So this is just, I just want to show you. So if you have a report to do, you could hypothetically do something like this. So you can basically say 6 to 6, which is that's can be this. That should be 1. So then would be the confidence interval as a word. So if you have that report and they say like the confidence interval is -3 to 6, and therefore we conclude X, Y, Z, you can automatize this and automatically print this as a PDF. You're changing your data frame. It's a new data frame. You're just running the same code on the data frame, will automatically change your entry on the PDF. Automatically create the PDF, and you just grab the PDF and you mail it out to your boss. That's how easy it can be. Okay, then we have absolute. Yeah, so this is just calculating now the effect size. We're doing this on line 23 or 22 on your code. We're basically calculating here the difference between exam1 and exam2. And we're dividing this by the standard deviation of both. Gets us essentially the effect size of 0.22. Simple, right? Relatively. Okay. So 10 point, any questions to that? There's a lot of stuff for you to play around. So the idea is really, I want to make this a thought-provoking exercise. And those of you that don't want to deal with it, don't deal with it, just run that thing down and submit it. Those of you that have an interest, play around with it. If you have questions, let me know. Yes?
Can you remind us how it's basically going to clear?
Copy and paste what?
You want to clear the console and copy it?
Yeah, not yet, not yet. We're not there yet. We have 2 more examples. Okay, but yeah, that's separate. Not a problem. Okay, same example here. We have score 1, score 2. Calculate the 95% confidence interval. Yeah, it's as simple as could be. So you basically difference. Basically, we can take this whole thing. No, let's not do it. Okay, differences is 1 minus this. Calculating now this. Calculating average. Calculating a standard deviation. (6.14). Now we're basically just calculating. So we have the difference now. The only thing we need now is the null hypothesis, which is easy, right? So it's score 1 minus score 2 equals 0. HA is this unequal 0. Now we need the standard error of the mean. This is calculated by standard deviation divided by square root of the sample size, which is 5. Now we just need a t, and the t is minus 7.8 divided by this, gives us minus 2.84. Since the degree of freedom is 4, oh, bless you, our critical value is now 2.78. So we know this is significant, so we're rejecting the null. Now the 95% confidence interval is basically lower limit, upper limit. Lower limit is basically now minus 7.8 minus critical value multiplied by standard error of the mean. Upper limit is minus 7.8 multiplied by 2.78 multiplied by plus is minus 0.16. So as we concluded, it's basically significant because it does not contain the 0. Effect size is now ES equals this divided by the standard deviation. Effect size is minus 1.72. If we set this absolute, it's basically a large effect size. Good, simple, right? So paired sample t-test, I think we're solid on that. So it really shouldn't be an issue. What's getting a little trickier is the independent sample t-test. So here the example is, okay, does watching award-winning fiction on television help us to understand other people? The psychologists tested whether people who watched award-winning fiction on television like Mad Men or West Wing performed better on a test of theory of mind than people who watched documentaries like episodes from the series Shark Week or How the Universe Works. After randomly watching either a fictional show or a documentary, they were asked to look at the series of 36 people, photos of people's eyes, and decide if each person was jealous, panicked, arrogant, or hateful. Scores reported from 0 to 36 are shown. Good. So we need an independent sample t-test. What is the comparison distribution? So what is the population? That's simple, right? So we know the population is here, population A and population B. We know the comparison distribution is now the comparison between the means, differences of means, the differences between means. So essentially what we're now doing is we're calculating first an average. Oops. Okay. So if we calculate the average first, we get 29, and we get now 27.5. So that's our average. So we see already the slight signal that was documented somewhat slower. but we don't know whether this is significant. So the standard deviation is now 1.5. Versus 1.2. The variance is consistently greater with fiction and smaller with documentary. So now we next need to understand what is the degree of freedom. Degree of freedom of TV fiction and documentary. So the degree of freedom here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So degree of freedom of fiction is 8, and this is 7. So now we know the degree of freedom total is now 15. The aliquot is now, the proportion is 15 divided, it's 8 divided by 15. We have 7 divided by 15. That gets us to the proportion. So now we get the actual proportional variance, the weighted variance. Now we get this. This variance of this multiplied by this, and this multiplied by the proportion. This now we're coming to the pooled variance. This is now the sum of this and this. Now we need the S squared difference. That's our pooled standard error of the mean. This is now this divided by 8 plus 1. Plus this divided by this plus 1. So now the S difference is now square root of this. So that's 0.66. So if you want to do a t-test now, and so first we need a critical value. The critical value is now 15. So this is the degrees of freedom. It's 2.13. So critical value is 2.13. So our t is now this average minus second average divided by our S difference. Gives us a t of 2.26, which is essentially a significant difference between both. So this is how you do an independent sample t-test. We can also calculate effect size. And we, of course, know all of this, but we have this for the sake of time. Let's focus on Excel. So we have now our, so that's this. We know now df2. We have calculated this. We know score 1, score 2. We know the p-value is 0.04. Confidence interval 0.17 and 50.4. Here I changed the order, so it's score 1 to score 2, so don't be in any way surprised to have positive results. It should be the same values, 0.17 and 15, just negative. Oops. And now 11.29, that's the example we have just looked at. And that's fiction versus, so here we have the mean, the standard deviation. same as we have calculated it. And now we're using the t-test function to calculate that. And that is a Wilks test now. And that basically gets us all this data quite in the same fashion. So again, the degree of freedom is 14.891 because that's the approximation. The t-score is actually somewhat consistent with what we found, 2.290. No, it's smaller. But that's for this more precise estimation. Confidence interval is shown here. And the comparison of means. So you're looking at a p-value that is smaller than 5%. Therefore, you will reject your null hypothesis. Good. Okay, practice lab 3 completed with 3 more minutes. Click on the console, press Control and L. Hear the whole thing. Go in somewhere in the script. Just click it once. Press Command and A or Control and A for the Windows users. And press Control and Enter and run the whole thing down. Excuse me. Then basically go to the last entry of the mean of y and select everything that you have ran now. Press Command and C and copy it. Then go on the Spotlight. Open Text Edit. Build a new document and copy all of this in. Go on Save and save this as Practice Lab 3 into the folder that you have created. What to put? So label it as STAT1021F, your family name, and the semester. It's spring, right? Practice Lab 3, not surprise. Practice Lab 3. Save it like that, and this is Practice Lab 3. Any questions? If not, have a nice evening.
Thank you.